Okay, thank you all. Yes, it's a pleasure to present these features. First of all, I apologize my spoken English and my accent, my French accent. So be indulgent with me, okay? So who am I? So I work for. I'm a support networks engineer. So at Orange. So this is Orange is it's a big company, but I'm currently working on the AS3215. So this is a French domestic and mobile backbone. So I work with big routers, especially Juniper and Nokia devices. We have some Cisco boxes, but only few. So I'm passionate by networking and all around networking. And for some times now, I also do some development. So mostly Python, but I'm currently learning Go. So it's a nice language as well. So I also wrote several Juniper Day One books and the MX series second editions. Okay, you can follow me on Twitters. I am a SpongeBob fan, just for fun. So, what is iMan? So iMan is not a Krabby Patty. Okay, it's a new sampling features provided by Juniper. So yet another next generation sampling solutions. No, it's not what we call the sampling young. It's more features that tries to leverage the best thing of other sampling technologies to build flexible and scalable monitoring solutions. And the aim is to offload all complex post-processing tasks on the collector side. So to summarize, you take IPFix, you take mirroring, you take SFlow, you put all these features in a checkers, and you have inline monitoring. So this is a current feature list. So currently, these features is only supported on MX. It should be available in few months. I don't know exactly, but it should be available also on PTX 10K. So currently, it's only supported on MX. So including the MX 10K, the new platform based on the universal chassis of Juniper, which is the same chassis as the PTX 10K. So this is supported on all MX platforms since Junos 19.4 and all line cards except ZT-ASICs, which is supported since 20.4. This is the latest Junos release. So it's currently supported on all line cards since 20.4 and also on VMX if you want to do some tests in virtual environments. So the aim is quite simple. It's like SFlow. You capture some packets from the Ethernet headers and you have a kind of chunk of packets. So from 64 bytes up to 126 bytes. So it's configurable. You can select the amount of bytes you want to capture line rate. And you can add metadata attached to the packets, to the captured packets. So these features currently provide input and output interface index, the directions of the capture, so ingress or egress, and the original packet size. This is what we call metadata. And the packets itself, so up to 126 bytes, and the metadata are put in together an IPFix container. So it's quite new because we use IPFix as transport protocol for this kind of mirroring traffic. So this is an IPFix containers, and we can leverage this IPFix templating. It's so easy to add metadata in the future because metadata, input, output, interface, index, directions, original packet size, are viewed like an IPFix template, okay? What is new compared with IPFix? There is no latency, no flow aggregation buffering. When a packet arrives and match the iMan configurations, it is captured and sent to IPFix. There is no flow aggregations. There is no MPC and PFE adherences. I mean, unlike IPFix, classical IPFix flow aggregations, you have to configure the sampling instance on the MPC itself, okay? And you can also only have one instance per MPC, per PFE. This is not the case with inline monitoring. There is no hardware adherences. So you can have several instances. We will see later what is an instance, up to 16. You can have several collectors per instance, up to 4 collectors per instance. And you can specify the sampling rate per collector. And it's quite flexible. Unlike SFlow, which is configured by interface, iMan is configurable through firewall filter. So you have the granularity to match some very specific packets and say that you want to send this traffic to the iMan collectors. So it's applicable on ingress or egress directions. It's currently supported for iNet and iNet 6 families, but we should be able to have other family in few months because Junipers have the roadmapped new families, and MPLS family will be added very soon. So it's a nice information. So currently it's only supported for iNet and iNet 6. And you can also configure which DSCP value, which forwarding class, and which routing instance you want to use for inline monitoring packets. So the packets, IPFix packets that send the captured packets. And you can combine in parallel with other sampling solutions, such as classical IPFix flow aggregations. So this is not too bad, okay? It's quite complete, and you can do some cool stuff with this feature. We'll see later what. So first, let's compare the several sampling technology available on Junos. There are some features that are well dependent. So you have classical mirroring, you have SFlow, you have IPFix, and you have now Inline monitoring. Okay, so let's compare with IPFix. So first, there is no latency. IPFix, depending on your configurations, you can have seconds to minutes of flow aggregations. So you can have some latency on the collector side. Other point to mention, it's inline. It's performed by the ASIC itself. If you compare to SFlow, which is close to inline monitorings in terms of mirroring packets, SFlow, it's done by the CPU of the line card. So you have some limitations. Currently, it's around 9K flow max per line cards. And currently, there is no limitations on the inline monitorings. I performed some tests I will show you later in last slide some figures about the performances of these features. So it's quite impressive. Okay. There are some few metadata. So compared to classical IPFix flow aggregations, there are less metadata, because with IPFix, you have sometimes to add metadata. I mean, you can provide some BGP informations, origin AS, destination AS. With inline monitoring, you offload this post-processing packet captures on the collector side. So on the collector side, if you want to enrich your packet sampling with other information, you can do if you want. And where SFlow use its proprietary encapsulations, where mirroring can use several remote mirroring solutions like GRE or L2 VPN. Inline monitoring use IPFix via a specific sections called data link frame sections. So this is this RFC that allow you to put in IPFix packet some raw bytes. And it's quite new features. So since 19.4 for all Junos, all Juniper MX line cards, and just for ZT based line cards, so MPC 10 and 11, it's 19.4, 20.4, sorry. And you can perform one-to-one packet mirroring to 1 to 16 million sampling rate. So why? Because it's one more new solutions to sample traffic. So why? I give you with this slide some use case that we should consider in a range. Not all, but some few use cases will be considered this year by Orange with these new features. So the first use case is what we do currently with classical IPFix flow aggregations. It's traffic monitoring accounting on edge devices. As I said, there are few metadata with iMan. Unlike classical IPFix, you have many metadata like BGP informations. But with iMan, you can you do not rely on the predefined IPFix templates. You can build your own template on the collector side, and you can extract what you want inside the packet. So you have access to the packet headers and some part of the payload. Case study 2 is security. It's a very fast solutions because there is no buffering, no flow aggregations. So we can detect very quickly, very fastly DDoS or malicious traffic without some latencies. So it's quite interesting, and we will consider this use case in a range because currently we use flow aggregations to detect DDoS attack. And sometimes we have latency between the start of the attack and the detections by our solutions. So it could help us to have faster detections. You can also identify complex attack. Unlike IPFix, where you have predefined templates provided by IPFix features, here you can parse, if you want, the payload, a part of the payload, because you don't have the whole packets. You have some few bytes only, but it's sometimes enough to detect some signature in the payload. So it could be interesting to some use case if you want to have some DPI, deep packet inception, light DPI. Okay. The use case 3, it's tier written channel. See, it's traffic engineering written channel. As you don't have latency, you can very quickly monitor traffic routing, maybe triggered by a controller, a traffic engineering controller. So it's a very nice telemetry channel, fast telemetry channel to monitor, for example, traffic routing in case, for example, of closed loop traffic engineering. You change the routing on your networks and you have the return channel. You see if this change in your network has some effect on the traffic. Okay. Use case 4, so payload analysis. You have 126 bytes, so you can have all the header, but you have some part of the payload. And usually it's enough to detect some good, some interesting stuff. For example, it can help you to detect if the traffic is encrypted. After the TCP header, you have the TLS header. You can check with by matching the TLS header if the traffic you receive is encrypted or not. You can detect some exotic unproprietary tunnels, for example. You can dump some specific packets for post-analysis, for example, DNS reply. Usually, these packets are small and 126 bytes are enough. Okay. One more use case, it's layer 2 accounting. As I said, the packet is captured on the layer 2. So you have the Ethernet header embedded in the IPFix container. So it could be very interesting for IXP, for example, networks, if you want to perform MAC per MAC accounting. And the use case 6, as I am a support network engineer, all stuff around troubleshooting. You can easily trigger a mirroring probe with these features. Okay, so if you want to catch some specific traffic, you can do that very quickly. So what else? I guess there are so many use cases, there are only few that we should consider in Orange. So I can say more, okay? How? So now we will see how to configure iMan. So first, you have to define, like IPFix flow aggregations, some templates. So here I created one template. So templates in IPFix are sent periodically to inform the collectors what it will receive. Okay, so you can specify the rate of the template every minute in my case, and the rate of the option template. Option template gives some information about the sampling rate. It could be interesting on the collector side to know the sampling interval. But usually you, on the collector, you configure manually the sampling rate. But it's possible to retrieve this information through IPFix. So in the template, we can see the template of the metadata. You have the input SNMP index, you have the output SNMP index, you have the directions, ingress, egress, you have the original data frame size, and you have the container that will contain the packets, the raw packets from the Ethernet header. One information that is very interesting is the observation domain. So in each packet, you have the observation domain ID. This ID can be used by the collector to identify the source, the origin of the traffic. So you can configure a part of the domain ID with the observation domain ID. It's just 1 byte. And after the MX build the domain ID dynamically based on the iMan instance index, based on the collector index, based on the FPC slot, and based on the local PFE ID. So when you receive an observation ID, a packet streamed by the MX with a given observation domain ID, you can deduce from which inline monitor instance, which collector, with which FPC or which PFE the packet coming from. So it's really interesting. So this is a template configurations. Here there is only one template. You can create more templates if needed. Then you have to configure the inline monitoring probe. So it's under service inline monitoring. Here you can create up to 16 instances. Here I created 2 instances. The first one, called my instance 1, you refer the templates previously configured. You can provide the maximum clip length, the number of bytes that you want to retrieve from the original packets, from the first byte of the Ethernet frames. Here is the maximum size I set. It's 126. So you can see that you have the possibility to specify the maximum clip length per instance. Here the clip length is 64 bytes. This is the minimum size. And then you can set, you can configure per instance up to 4 collectors. In this instance, there are 2 collectors. So you specify the source address, the destination address of the IPFix packet. It's UDP by default. You can specify the UDP destination ports and the sampling rate. Here, I want to sample every packet. Here, I want to sample 1 packet every 1,000 packets. So you can set up sampling rate per collector. So it's very interesting and more flexible than classical IPFix. So you have defined your instance, your collector per instance. Okay, now you want to apply, now you want to monitor some packets. So I also provide more information about the collector config. As I said previously, you can configure the DSCP values, the forwarding class assigned to the iMan packet. And if you want to send these packets, these iMan packets through a specific routing instance, you can specify the routing instance name there. And then on the operational command, you can have some statistic if you issue the show service inline monitoring statistic and the FPC number. You can see the number of packets received by the PFE, and you can have some information about the number of packets sent to each collectors and per instance. So now I want to configured my iMan probe on some interfaces. So here it's my previous iMan configurations. Now I find firewall filters that refer to iMan instances. It's a very simple firewall filter. It's a IPv4 firewall filter. You can do exactly the same with IPv6 firewall filter because it's also supported for IPv6. So here is the first term, it's called DNS. I want to filter only DNS packets. So the signature is UDP for 5053. And if the packets match this term, I say, okay, send this packet to the inline monitoring instance, my instance 1. When I say that, it means that the packets captured by the firewall filter is sent to collector 1. Every packet are sent to collector 1, and one packet every 1,000 packets are sent to collector 2. For example, it's a very fine analysis, and here it's just for global statistic, for example. Then I have also a second term, which is check TLS. So I want to match protocol TCP UDP for 443. So usually this port conveys TLS traffic, and I want to have some statistic about TLS traffic. Okay, so I send these packets to the instance 2, and the instance 2 is this collector. So I define the firewall filter, so which term match which kind of traffic, and then we apply the inline monitoring instance, the specific inline monitoring instance. So then you can apply your firewall filters in both directions, input, output, for both family. It's another firewall filter. You can use these filters in chain filter list by using input list, output list. So if you want to use this syntax, imagine you already have firewall filters apply on your interface. So you want to apply a specific iMan filters. So you can change your firewall filter by using input list or output list. So if you want to do that, you need to, the last term of the iMan filter should be then next term, to then go to the other term. So you can apply it through classical input output statements, through input list, output list, or if you prefer to apply on all the device, you can apply it on a forwarding table firewall filter. So at this level, forwarding options, family iNet or iNet 6, filter input or output. So beware, because if you sample your iMan traffic, you can trigger a sampling loop. So the best way to avoid this kind of bad situations, I recommend to define a very specific term, maybe the first term in your firewall filter, that say if you match UDP, in my case port 6667, then you accept the traffic and you configure nothing else. Because if you match an instance and you resend back the traffic that embed your packet, your captured packet, you will trigger a sampling loop. So beware with this. Some information about the metadata exported. with the packet. So about input SNMP and output SNMP. So you have some different type of interface supported. So you have a classical physical interface, GE, XE, ET. So if you apply on ingress interface iMan, so the input SNMP is the if index of the ingress interface, and as you apply it on ingress, you don't have output informations, so it's 0. But if you configure the iMan on egress side, you have on SNMP, input SNMP, you have the if index of the ingress interface, and with the output SNMP field, you will retrieve the if index of the egress interface. So you have the same for AE, but for AE on ingress directions, on the output SNMP, you will retrieve the child link of the AE. And for the IRB, on the output, you will retrieve the if index of the ingress VLAN bridge encapsulated interface. Okay? So it's good to know. So it's a kind of mirroring solution. So beware with, be careful with the traffic generated by the iMan. It depends of several parameters. So the first one is the clip size. So the maximum clip length you have configured between 64 bytes and 126 bytes. And it usually depends on the current frame rate of your traffic. For example, if I have an interface with 14 million PPS of traffic, and if I configure a sampling rate of 8,000 with a clip size of, with the maximum clip size, to compute the iMan traffic generated by the router, in this case, you have to take your maximum PPS rate of your interface. In my case, it's 14 millions. You have to divide by the sampling rate, and then you multiply by the number of bytes. So there are 74 bytes of header, so Ethernet header, IP header, UDP header, and IP fixed iMan header, plus the clip size. So in my case, it's 126, and you multiply by 8 to have bits per second. So in my case, if I use a simple iMan instance with these parameters, the router will generate 2.8 megabytes per second of traffic. So this is, we saw previously the template. Here it's the real IPFix export packet. So you have now the information. So in my case, it's an iMan probe configured on ingress directions. I can retrieve the if index of the input interface. I don't have the output interface as I configured iMan on ingress. I have the original frame size. So here it's 651 bytes. And here it's into the data link frame section. This is the raw packets. Data, original packet size, and Ethernet frame. So you can see, yes, it's 0x800, and this is the signature of IPv4. So here it's the beginning of the Ethernet frame. So this is destination MAC, source MAC, Ether type, and then the IP header. So some tests now. So I carried out some tests in lab, currently only on EA-based line cards. So on MPC9E on an MX2K. So EA means a PFE of MPC789. This is also the PFE on MX204, and also this is the ASICs that we can have on two kind of line card on the MX10K. Okay, so I only test on MPC9E, but as this feature is only a PFE based features, it's relevant to say that this test will be the same on all these kind of line cards. So to test iMan environments, so I load a 100 gig interface around 100% with a mixed packet size, so around 40 millions of PPS. I configure two collectors, one with a sampling rate of 8,000 with a clip length to the max, and a collector that sample all packets. So the 40 millions of packets per second, with the maximum clip length as well. And on the same interface, I also configured a classical IPFix flow aggregations. The firewall filter that which kind of traffic I want to monitor was very simple. There is no match condition. All packets should be processed by the iMan features. So it's just a pure accept, then inline monitoring instance, my instance. I tested this feature on egress and ingress with and without filter chainings, which means with input list and output list, but also with classical filter configurations with the keyword input and output. And I tested these solutions with iNet and iNet 6 family. It means that I send first 40 million PPS of IPv4 traffic, and then I perform back the same tests with 40 million PPS of IPv6 traffic. So the conclusions are quite good. It's line right. There is no traffic impact, which means that the traffic, the 100 gig of traffic did not encounter any loss. There is no performance degradations, no CPU memory impact. And for your informations, on the collector 2, where I sample all the packets, the traffic generated by the PFE was around 20 gigabytes per second. So if you want to collect this traffic, you must have a big collector. So this is not, it was not the case to decode this traffic on the collector side. The aim of this test is to test the PFE itself, okay? So we can see with this test that the PFE is able to generate 40 millions of PPS of iMan traffic, which represents around 20 gigabytes. They are less than the 100 interface because we only take 126 bytes of the packets. Next step. So these presentations, it's too early to have all the tests done, but because I'm currently performing some tests in my lab, I need to do the same test with our legacy XL baseline card, so MPC6E, and we have to do also the same test with our new ZT baseline card, so MPC10 and 11. I also have to test to apply iMan configurations through a forwarding table filter. And then we will plan a pilot phase in our live network on some edge device. But to do that, I need to work on the collector side because I did not perform test on the collector side. For this test, I use PM Act collector. We will see just after some part of configuration of the collector. And maybe I could try to enhance GoFlow, which is a very good open source IPFix collectors. So currently, it only supports classical IPFix flow aggregations. But why not? Maybe when I will be better in Go, I'm motivated to try to enhance this very cool open source collectors with to support data link frame sections with similar primitive features that PM Act have. And maybe if you have some advice of good collectors, a good IPFix collector that could support this specific encapsulations. Because if we now focus on the collector side I use in my lab, so I used PM Act in lab. It's with a Docker image. As I said, I did not perform stress test of this collector. Maybe I should do if we, because maybe we could do this collector in live networks, but I have to do that. And we have a specific plugin because this collector is has a lot of features, and there is a specific plugin to support IPFix. And the cool thing, this plugin supports the RFC that allow you to create your own parser to decode the data link frame sections used by the Juniper iMan features. So it's just few examples how to use this collector to decode some iMan traffic. So I run my collector through a Docker commands. So I specify the destination UDP ports. I specify one volume that map my IPFix collector configurations. I specify a second volume that match my decoder, which is called primitive, my decoder, my own decoder with this file, and I provide also another volume to catch the traffic exported by the collector. So this is a simple IPFix configurations. So my ports, some buffer informations, and I said that I want to use some not well-defined, well-known field, but you want to specify that you want to use a kind of parser that we will that say to the collector inside the data link frame section which field you want to extract, okay? And then I say I want to aggregate the traffic that I receive from IPFix based on this field. But this field are not well-known field. This field are the field that I build myself with the simple primitive config file. So here, it's a simple primitive config file that I build that help the collector to extract some field from the raw packets embedded in the data link frame sections. So it's very simple. I create a new field that I called MAC destinations, and I say to the collector, extract from the packet the first 6 bytes and convert this information as a MAC field. Then for the MAC source, I say, okay, start the packets, put an offset of 6 and catch the 6 bytes after an offset of 6 bytes. And this is the source MAC address. And so on. I do the same for IPv6 source address, IPv6 destination address, next header field, UDP source, and TCP source. So it's quite complex, but the documentation it's pretty good, and you can refer to those 2 links if you want to more information about the primitive configurations. So it's quite interesting because with these simple configurations, I can extract and aggregate the traffic coming from the data link frame sections. So I can build my own template. And then the output is just a simple JSON file. So I can retrieve what I ask to have. So my MAC destination address, my source destination address, my IP, and the source and destination ports, and some aggregate information. So I receive 2 packets coming from this tuple. The byte or the real byte size coming from the packet, the original packet size field there. Okay. So it's pretty cool, and it works pretty well. I don't know if it scales. I should do some tests with this very cool collectors. And you can easily, with this collector, enrich with BGP informations if needed. So it's quite interesting. And I am finished. I hope it was clear. Again, sorry for my English and some mistake, I guess. If you have some questions, don't hesitate.
Thank you very much. I was especially impressed by the demo slide you had. I didn't expect it to work with 100 gig line rate, and that's so well.
Yes, it's quite impressive because the PFE itself, after it depends of your fabric bandwidth, it depends if your PFE is overloaded or not. But it's not a real scenario to sample 40 millions per second of packets. So it's just to be sure that there is no side effect on the PFE with the maximum configurations. So it's pretty cool, and I'm pretty sure we have we will build some very interesting use cases. So yeah.